continue with the section 4.7 optimization. I was saying a few moments ago that there's really an infinite number of questions that you could call optimization, and there's no way that you can do that. So what we're really doing is giving you tasters of types of questions, little families of. The ones that we've been focusing on mostly so far have been ones involving rectangles. So we're going to stay on that theme for a little while longer, and then we'll move to questions where you're given a formula, and well, we'll see where we go from there, because there's a lot in that. So this one is a version of question 7, and what it says is that you've got a square 3x3 piece of cardboard, and you cut little square corners, these guys here. And once you cut those out, I guess I'll shade them to kind of emphasize that they're cut out. What you then do, don't know if you've ever done this in school, actually I've not, but if you bend them along these dotted lines, right, so you bend up the sides, you bend up the sides, you will make an open-topped box. That's not bad, right? And we are on the quest of finding the box with the biggest volume. So we're after the box with the largest volume. Now that's important when you do optimization questions, because there's always going to be something that you're trying to make the biggest it could be or the smallest it could be, right? That's the optimization part. And that formula, whatever it is your optimization function. That's the thing you want to get in terms of X. So now I have to go and I have to put in some variables, things that we don't know. Well, if you imagine that the distance from here to here is Y, and that each of these little squares that we cut out are X's, then we've got the beginnings of calculating this style. Well, when you cut the corners and you bend them up, won't the height of the box be X? Won't that be if you bend it up? Do you see what I'm saying? The height is X. And I'm going to call this distance here Y, and I'm going to call this distance here Y. So the volume of the box is going to be its length times width times height. And so the volume of this box is going to be Y squared X. So far, so good. Now, I need to make sure that this finishes out being only X's. And if I look at my picture and I look at the distance I call Y, is it that distance? There, right, Y. Can anyone tell me what Y is in terms of X?
3 minus 2x.
You nailed it. You want to tell everybody else how you figured that out?
Just looking at the, yeah.
So you saw that bit was 3 and you took away 2 X's, and that's what that is. Okay. So what we now have is our optimization function. I like putting the X first, and instead of the Y, we got that guy. So your goal is typically to find this function, because once we know that, this particular function represents the volume, we can then find the largest or the smallest. You know, depends on the question. So I'll rewrite the volume. It's x 3 take away 2x squared. Now to maximize this, find the derivative. And when the derivative is 0, you're going to get the biggest answer. So well, let's use this notation. I've used this for a while. dv by dx. What differentiation technique or rule shall I use to differentiate this guy?
Product rule.
Product rule. So if I put this f, and I call this slot j, you get f dash j plus f of j dashed. So it's 1 times 3 take away 2x plus x times. Now, if you differentiate this guy, it is 2 lots of 3 minus 2x to the power of 1, but it's also a chain rule. So it's not just this, it also has that inside function. So you get times an extra -2. Now, if you pull out 3 take away 2x as a common factor, you will be, there we go, you will be left with the 3 take away 2x minus 4x, and you'll be left with a 3 take away 2x and a 3 take away 6x. That looks good. Now we need to solve when is the derivative 0? And it looks like we're going to get 2 answers. If you solve this one, x ends up being 3/2. And if you solve this one, x equals 1/2. Well, you can't have, well, I'm not saying you can, but it's unlikely that you're going to have 2 different correct answers, right? One of them is going to be the biggest answer it could ever be, and the other is probably going to be the smallest volume it can ever be. I'm killing that one. And you might say, well, what's wrong with 3/2? Let's go back to the story. If you had a box that was 3 feet by 3 feet, and you cut 1.5 inches out of this side, and you cut 1.5 inches into that side, wouldn't the box disappear on you? Because 1.5 and 1.5 adds up to the whole thing. It's a bit like you just did a big cross and threw away all the paper, right? That's what that one is. So here's your optimal value. So that means the dimensions, length, width, and height. Well, the length is called y, the width is called y, and the height was called x. So the x is 1/2 foot, and y is 3 take away that, so y is 2 feet, and y is 2 feet. So if the question wants to know the dimensions of the biggest box, you will say it's 2 feet by 2 feet by 1/2 foot high. If the question says, what does it ask? Because it's important. And if it asks, what is the maximum volume, which is what it asks in this case, you will go 2, that's it, that's why, times 2, times 1/2, and you will get 2 cubic feet. So you kind of make sure that you read what do you want. Actually, I need to find these 3 numbers before I can get that, but that was what they asked for. And that is the end of that rectangle question. Any questions about that process? The goal is to get the optimization function, right? Your goal is to find this guy here in terms of x. Right, let's look at our next one. Question 8. A farm wants to fence an area 6 million square feet. Wow. Okay, we're going to be dealing with big numbers then. And he wants to, this area has to be a rectangle that he has split in half with another fence. What should the lengths of the sides of the rectangle field to minimize the cost? So we want the minimum cost. So he's building a field with fencing. We know that the area is this, and we have to minimize the cost. Okay, let's start by putting things we don't know. I'm going to call that total distance from there to there y, because I want to. And I'm calling this one x, because I want to. And the reason I'm putting those as x and y is because you told me up here that the area, which is x times y, is 6 million. And what that does, it allows me to find y in terms of x. So I'll put a little bubble around it because I'm going to use that later. Now, when they talk about minimize the cost, they could have just said the smallest amount of fencing that you could get, right? Because that's what you're buying, right? You're buying fencing. So if I wanted to figure out what the total amount of fencing is in building this rectangle, it would be two sides, so I'll call it perimeter. Two sides, both y units long, and 1, 2, 3 x's. Does that make sense? That's the total amount of fencing, right? One at the top, one at the bottom called y, 1, 2, and 1 in the middle called x. So there's 3 of them. That's the function, the optimization function, right? Minimum cost is this. And now I'll bring this guy into play. That's y. So we are looking at, now it's 12 million. There's the optimization function. That's our goal, because once you get to that, no matter where the story led you to, once you finish at this point here, aren't you just going to differentiate it and find out when the derivative is 0, typically? And that's going to be the size that x needs to be. And then when you plug x into here, it will also tell you the size that y needs to be. And so I'm just going to stop there. You can differentiate it and find out what the x is. It's actually a nice number, but it's on the big side. Question 9. A rectangular storage box without a lid is to have a volume of 10 cubic meters. Okay. That's another one of those boxes, right? Open top. You're told that the volume is 10 cubic meters. And that the length of the base is twice its width. So if I call this guy 2x, and I call this guy x, haven't I made its length twice its width? and I don't know that guy, so I'm going to call him Y. Now, it gets a little bit messier. You want to make this box, the base, the floor, is going to cost you $5 per square meter. And if you want to build the sides, they're cheaper. They're going to be $3 per square meter. And here's the kicker. We want to minimize the cost. So that's going to be my optimization function, right? But there's a lot to do before we get to this guy, right? So let's kick in with this piece of information. I know the volume of this box is length times width times height. So that's going to be 2x times an x times a y. And I know its volume is 10. So we have 2x squared y. If you divide both sides by x squared, are you comfortable about how we found what y is in terms of x? Right, divide 10 by 2x squared and then cancel it down to 5 over x squared. Right, cancel the 2's. Now the cost, that's going to be a bit of a thinker. It's going to be $5 times the area of the base plus $3 times the area of the sides. Okay, what is the area of the base in this box here? What is the area of the base?
Two x cubed.
Are you sure about cubed, or do you want to reduce it to squared?
Oh, squared, yes.
If you look at the base, I don't want to shade it, mess my bits up, but the floor, you see the floor, it's x times 2x. That's cool. So 5 times that area. Now the next one's messier. If you're talking about the sides, there's 4 of them, right? There's one here, there's one here, there's one here, and there's one here, right? Now, this side here, isn't its area 2x times y? You see that rectangle? 2x, 1i. So that's 2x times y. And if you do this side here, isn't the area x to y? But that one over here is the same as that, and that one over here is the same as that. So you get 2 of them that look like that, plus 2 of them that look like that. Are you happy about the area of the sides then is 2 lots of 2x times y and 2 lots of x times y, right? One for here and here, one for here and here. Now I'm going to tidy that up a little bit and multiply these while we're at it. 10x squared plus 3 lots of 4xy plus 2xy. That gets you 10x squared plus 6xy. And that gets me 10x squared plus 18xy. I'll call that guy C. I tend to do these questions here, you know, the optimization function at the start in terms of y. And the reason I tend to do that is it tends to make it nicer looking. But there will come a point, which we've reached, where that guy there has to be turned into x's, right? This y. And the x's it's going to be turned into is the guy we found way back here. So it's going to be turned into 5 over x squared. So we have 10x squared plus 18x and replace the y by 5 over x squared, which now gets us 10x squared plus 90 over x. And we have got to the destination we always want to get to. Here is our optimization function. Now, won't we just differentiate this and find out when it's equal to 0? And we will have our ultimate, you know, the value of x that gives us the ultimate box. Right? And if x happens to be 5, that'll be 10, that'll be 5, and that'll be whatever 5 over x squared gets us, and we are done. Do you want me to, can I stop here, or do you want me to do the differentiation bit for this one? Okay, move on. Okay. The key to doing an optimization question is to find that optimization function. Okay, so let's change tack. Let's forget about boxes for a while. We've done tons of them. And let's look at a question like 6 and 7, where they have actually given you the formula. So you don't need to do anything as far as creating an optimization function, because they give you it. This formula here tells you the rate at which photosynthesis will happen for a particular species of plankton in a place where I is basically the amount of light. So obviously, if I is big, you'll get a lot of light, and therefore you'll be able to produce a greater amount of photosynthesis, and that's fine. And if you're not into photosynthesis or biology, it's still fine, because our job is to find out, essentially, the best value for I for maximizing photosynthesis. Evidently, if there's too much light, if it's too bright, and I'm assuming when it's too bright, it's probably too hot either. A lot of plants don't actually do as much photosynthesis because aren't they trying to protect themselves from being dehydrated and burnt? So some plants have different protective mechanisms. Some of them actually just curl up. So, you know, there's very little of them exposed to the sunlight. So let's figure out the optimization value. What's the best value of I to get the most photosynthesis? I hope you all recognize this as just an ugly quotient rule, but not the worst one in the world. So it's an f dash g, take away an f g dashed over g squared. If you differentiate the top, you get 80. You leave the bottom alone. You get that. Minus, leave the top alone, and differentiate the bottom. And that's 2i plus 1. All over the bottom squared. Now, we have style points. I'm going to try and make this as pretty as I can. Distribute the 80. So I now have 80i squared plus 80i plus 80. Take away that times that is 160i squared. Take away 80i. If you do that guy kills that guy off, you're going to be left with 80. Take away 80 I squared. Dun, dun. That's not a 1. Yes, it is a 1. What are you talking about? I don't like my answer. Yeah, that's fine. When you pull out 80, okay, I like my answer now. It looked weird, but it's good. We need to solve when is the derivative 0, which basically means when is that guy 0. And I just realized that I didn't do the best that I could do. There we go. Isn't 1 minus I squared the difference of 2 squares? So it looks like we have 2 answers. But you can only have 1, typically 1, correct one. I'm keeping that one, and that's the correct answer. And I'm killing that one. Why am I killing that one?
Because photosynthesis wouldn't occur with negative light.
Yeah, in fact, I'm not even sure what negative light means. I think I equals 0 means there's 0 light, right? There's no light at all, it's pitch dark. So in a lot of ways, isn't that just a nonsense answer, right? It doesn't even exist in reality. So sometimes you have to pick. And in this question, then I go and read what they want. I is 1 is what they wanted. Yeah, but they wanted to know what the value was. So you have to find out P of 1. So it's 80 times 1 over 1 squared plus 1 plus 1, which is whatever 80 thirds is, right? There's your answer. And I was actually wrong. It's 6 and 5, not 6 and 7. And in question 5, they do a very similar thing, so I'm not going to do that one. They give you a formula, and you have to maximize it. And the only thing that makes it a little different is they had the little k, which is just a constant that you treat as if it was a 2. Done that one. So let's move on to another puzzle. This is a version of question 10. Nothing to do with boxes or rectangles. But in this question, you are given a straight line, y equals 2x plus 4, which is roughly, very roughly, that red line. And you want to find the point that's on that line that is closest to the origin. So here's the origin. Now, can you imagine that that point might be 4 units away, and this point away down here, that point there might be 8 units away. Isn't there probably a sweet point somewhere around about there? I'll call it P. That's the closest point to that line. That makes sense, that there is probably going to be one point on that red line that's closer to the origin than any of the other points. So far, so good. Now I'm calling that point x comma y, because I don't know its coordinates. And we are trying to minimize the distance from the origin to the point P. So we're trying to minimize the distance OP. Now O is the origin, and P is the point x comma y. And I'm going to call D the distance. Now, does anybody know how you find the distance between 2 points. Don't worry about one of them's got X's and Y's in it. Pretend it's 1, 2 if you like. How do you find the distance between 2 points?
Isn't it the square root of x2 minus x1 minus y2 minus y1?
Oh, so close. Plus,
Oh, yeah.
but so close. That'll do. And I'm running short of colours here. We'll call that guy x1, y1. You could call that guy x2, y2. But essentially, you've got d equals the difference in the x coordinates squared plus the difference in the y coordinates squared, which in this case just becomes x squared plus y squared. And this is our optimization function, right? This is the guy that we want to be in terms of x, because once he's in terms of x, then we are kind of good to go. And I'm going to do a little cheat at the end, but I need to know what y is in terms of x. Somewhere in this picture, there's a piece of information that will allow you to turn y and write it in terms of x. Can anyone see where it is and what it is? Somewhere up here.
2x plus y. The 2y equals 2x plus 4, sorry.
Yeah, I know what you meant. Yes. You agree? Now you might say, well, why is that the case? If you are a point that's on that line, won't your y coordinate be 2x plus 4? Won't your y value be equal to 2x plus 4? You see? Now, I'm going to make this a little bit tidier, style points, but not much. It's going to be x squared. If you FOIL that out, you're just going to have to trust me right now. You're going to get 4x squared plus 16x plus 16. If you combine all the like terms, you're going to get 5x squared plus 16x plus 16. So we have our optimization function. And you could, and there's nothing wrong in doing that, couldn't I then just differentiate this and find out what value of x makes its derivative 0, and boom, Bob's your uncle, we know the x coordinate, right? And then we could do y equals 2x plus 4 to get the y coordinate, and we will have finished the question. But I'm going to show you a little trick that you can choose to do or not. Differentiating this guy is possible. You agree it's a chain rule and it's a little bit ugly. So I am going to say this. Suppose I square everybody. Won't the value of x that makes this biggest be the same value of x that makes that the biggest? So basically I'm finding the value of x that makes the square of the distance largest, which is going to be the same thing. But differentiating that's easy. So that's my little side ship. So let's return to the other question, the other optimization, and use that one instead, because I did not like the what did you just do look. So I'll call it that. You want to differentiate it. You multiply by the power and you divide the power by 1. And then you times by the inside function, which is what, 10x plus 16. And this guy comes downstairs and turns into a square root. And a half times this guy gets you 5x plus 8. And now you want to solve. When is the derivative 0? Which really just becomes when is the numerator 0? Which then becomes that guy. Which then becomes that guy. And the y coordinate is 2 times the x coordinate plus 4. That's 16, 20, I believe. That's positive 4/5. And so the point that you're after has coordinates negative 8/5, positive 4/5. And yeah, that looks about right. Now, if you had done my shortcut, if you differentiate this guy, you will get 10x plus 16, which if you then divide by 2, you get this guy and you're finished. So all my guy done is it went from here to there without this messy stuff. So you can choose which route you want to take, but both of them solve the same problem. Okay, you're hanging in there, guys. Any questions? Each one's got its own little thing going on, right? Here is a particular shape of a window. Called a Norman window. So it's basically a rectangle with a half circle stuck on top of it. And if you didn't know that was a Norman window, now you do. And in this picture, they're telling you this guy is X. And they also tell you that the perimeter is going to be equal to 8 feet. And we're being asked to find the greatest amount of light that is emitted, which is just another way of saying maximize the area of the shape. Because the bigger the area, the more light that comes in. Now, if I add an extra little invisible dotted line there and call that X, would you agree that the diameter of this half circle is X? Now, I don't know that distance. I'm going to call it Y. And I'm going to work on this piece of information. And this guy has got one job and one job only. Tell me what Y is in terms of X. That's what I use them for, right? Find out what Y is in terms of X. Now, this dotted line here is not part of the perimeter. It's just to give you an idea of the shape. So if you look at this shape, it's made up of Y plus X plus another Y on the other side plus half a circle. Just that bit. These two get you 2Y plus X and half a circle. Right, what's the formula for the circumference of a full circle? What's the formula for the circumference of a full circle?
2 pi r.
And not normally 2 pi r. There is another formula that perhaps a little bit easier in this context to use. So 2 pi r is correct. What's the other one?
Pi times the diameter.
Okay. So the circumference, which is the distance around a complete circle, is pi times the diameter. So if it's half a circle, won't it be a half pi times d? right? Half a circumference, half a circle. And diameter is x here, so that ends up being 1/2 pi x. Are you happy about how I got the half circle's perimeter? It's half of pi times diameter, half pi x. And we know that this guy here is 8. So I have 2y. Well, I'll just write them the way they are. And x plus 1/2 pi x. Now I need to solve for y. Okay, tell me what to do. What do I do to both sides to eventually get y equals?
-8.
I'm trying to think if that's worthwhile. It might work, but I choose not to go that way. Remember, you want y on its own. So if you get rid of 8, all you're doing is moving everything over here and you've got 0 there. So I'm thinking
then-
that's probably,
Then you'd move the y over to the other side.
and then it would work if you wanted to do it that way. Yes, then that's totally fine. But I'm just going to avoid negatives. So I am going to take away, so what you said is perfectly correct and it will work. But I'm going to do it that way. Just because I want to avoid -2y equals negative stuff. Because when I have too many negatives, you know, I tend to lose them when I do the last step. You know, something ends up plus when it shouldn't be. So I try and avoid them when I can. So same idea as yours. I'm just going to subtract an x from both sides and 1/2 pi x. And then I only need to divide everybody by 2. So this becomes 4. This becomes -1/2 x. And this becomes -1/4 pi x. That is one ugly version of what y is. Are we good with that? How we finally got y in terms of x? So back to the question. We want to maximize the area of this shape. Well, the area of this shape is made up of a rectangle, x times y, plus half a circle. This time it's the area of half a circle. So it's going to be x times y plus 1/2 pi. And it's not pi times x squared. What is the radius of this circle on the top if it was a full circle?
x1/2.
All right, so we will say 1/2 x squared. So A for area is xy plus 1/2 of pi, that guy squared. So pi times 1/4 x squared. So the area is going to be xy plus 1/8 of pi x squared. And then the area is going to be x times that ugly guy plus 1/8 pi x squared. So let's see what we have. The area is 4x. Make it more clear. Take away 2x squared. Take away 1/4 pi x squared. Add 1/8 pi x squared. So it's 4x. Take away that guy. That and that gets you, I almost got my sign wrong, -1/8 pi x squared.
I think this will say a 1/2 instead of a 2.
What's 1/2 inside of 2? What did I
The
do wrong?
negative
Oh, this
2x
here.
squared.
Right, let's check that. 4x minus 1/2 x squared minus 1/4 x squared plus that. So what do you think might be wrong? Or if I fixed it?
No, you fix it now. It's good.
Okay. So that is a half. Phew, that is one ugly looking optimization function. So I'm now going to differentiate it. That guy gets you 4. That mess gets you -1/2. And this guy gets you 2 times that is -1/4 pi x. And I want to solve it. So that's what I'm trying to solve. I'm going to subtract 4 from both sides. Yeah, I'm definitely generating an awful lot of negatives here. So why don't I multiply everybody by -1 so I don't need to worry about negatives. And then I'm going to do that. I have a half x and I have this ugly amount of x's. So if I combine them, that's how many x's I've got. Which means I can now get x. So what should I do to both sides to find x?
Divide by the term connected to the x.
Which is, in anybody's view, one ugly looking fraction. You agree that is not pretty. We don't like fractions with fractions in them. So I'm going to make that answer nicer. So this is the guy that we've got. I'm going to multiply by a special version of 1. And the one I'm picking is 4. Because 4 gets rid of halves and 4 gets rid of quarters. So 4 times 4 gets me 16. 4 times that guy gets me 2. And 4 times that guy gets me pi. And that's all they wanted to know. What value should x be? And the answer is make x 16 2 plus pi. And that's all we have time for today. So last name and bye-bye for now. Oh, and before I forget, this is week 9, as you know, but there are no more extensions. This coming Sunday, any homeworks that are due need to be done because I need to close the book, add up all your scores and get them ready for the final exam, which is next week.